Hello, my name is Tautvydas Liorančas. I am from Vilnius Tech University, Antanas Gustaitis Aviation Institute, and today, on behalf of ECOCORK project, I will be presenting to you about the manufacturing and implementation of cork-based composites in aviation. It is vital to examine the most significant positive and negative properties of cork-based composites to determine the use of natural cork-based composites in aviation and their rational implementation in the structural elements. This research provides a broader approach to cork material manufacturing processes and the application areas of cork-based sandwich structure composites in aeronautics. Cork composite applications for gaskets and other sealing materials are also presented in this chapter. In this chapter, you will see the following topics: an overview of cork-based sandwich structure composites, cork-based sandwich structure composites manufacturing methods, cork composite applications for gaskets and other sealing materials, tests of sandwich structure composite materials with cork fillers, and also bending tests of cork-based sandwich structure composites. Chapter 4.1: an overview of cork-based sandwich structure composites. First of all, we will talk about the definition and types of sandwich structure composites. Sandwich structure composites are fabricated of several layers of different materials, and you can see such a material in the picture on the left, where you can see the inner core in the middle and the stiffer sheets attached to the top and the bottom of the core. Sandwich structure composites, in which two face sheets are attached to the core, are most commonly used in aeronautics. To understand the reason why it is so commonly used in aeronautics, we should look at the picture on the right, where we can see that by making a sandwich structure, we increase the weight of the material very slightly, but we can increase the stiffness very significantly. To understand the cork material better, we should first look at the properties, advantages, and disadvantages of the most significant cork-based sandwich structure composites in aeronautics. One of the most commonly known advantages is cork's environmental friendliness and recyclability. Furthermore, this material has good noise and vibration dampening properties. Also, it has very good fire resistance, which is a very important characteristic in aeronautics, since all materials used inside the aircraft cabins have to be fire resistant. Also, we must not forget its aesthetic properties. Furthermore, it is resistant to moisture. It has very good thermal insulation. And also, very importantly, it is well treated by conventional machinery methods. It means that we can use already available tools and methods to machine and create parts from cork. However, there are some disadvantages. For example, cork material has sensitive mechanical properties. It is because of its natural origin. So depending on the tree, depending on the season, depending on various environmental factors, you may have different properties in a similar material. Another disadvantage is low resistance to mold and other fungal damage. In aeronautical engineering, we are not very oftenly dealing with natural materials, so mold and fungus can be quite a factor when dealing with cork. And one more disadvantage is untested or unproven resistance to other chemical materials. And as we know, and as we will discuss later, in aircraft, we are using various chemicals, fluids, fuels, hydraulics, and this is a very important factor when discussing about cork-based composites. In the following chapter, we will discuss the application areas of cork-based sandwich structure composites in aeronautics. Following the defined advantages and disadvantages of natural cork-based composite materials, it is possible to estimate which aircraft structural elements could be manufactured using sandwich structured or multi-layered composites. From our experience, there are parts in aircraft that are very commonly replaced. For example, glider winglets, small aircraft wing leading edges, or wing tips. These parts are very commonly damaged, and they're usually made from composites that are non-recyclable. So this is where a composite material could play its role very well because it's eco-friendliness and recyclability. Furthermore, we see a very clear implementation of corks in aircraft cabins. For example, in the picture on the right, on the aft back side of the aircraft, you can see bulkheads that are separating different aircraft areas. And these bulkheads are currently being produced by using wood material. However, because the material needs to be both lightweight, it needs to be sound isolating, and it needs to be fire resistant. So we can clearly see that this is a place where cork would use all of its advantages. And moreover, we must remember that cork has very good aesthetic view. So aircraft cabins is a place that cork material could be used very widely. Now that we have discussed the properties of cork-based materials, we can talk about the manufacturing method of sandwich structure composites. One of the most common type of sandwich plate is a simple flat plate, as you can see in the picture on the left. While applying mechanical compression for the sandwich structure panels, flat panels with face sheets consisting of pre-made sheets of metal, wood, plastic, or other materials are the best option. As you can see in the picture on the left, to manufacture a flat plate, you must select your face sheets, your cork core material, an adhesive that will bind these two materials together, and you need to apply some compression force that will allow these materials to stick together. On the picture on the right, you can see a more sophisticated method, but it is proven to be very well tested, and the results are very satisfactory. So the manufacturing method is to put your manufactured material into a vacuum. The vacuum applies compression force that binds the two materials together, and also it removes any excessive adhesive that you use during the process. However, the production is not so simple because the core materials are very light and had very low contact stress. The face sheet materials are usually characterized by having good mechanical properties as well as relatively high contact stress. As you can see in the picture on the right, the face sheet material is usually very thin, while the core material is quite thick. However, the contact stress is quite low. So in the picture on the left, you can see the most commonly used solution. If you have to mount your plate somewhere or attach it somewhere in the aircraft, usually engineers put an insert during the manufacture process. The insert has a stiffer material that has higher contact stress. Therefore, you can apply higher local loads in this area. Very similar strategy is used when you have to attach your sandwich panels with bolts. Then you need to install an insert during the manufacturing process. The insert will be able to withstand the high local loads that appears in places that are bolted. And furthermore, if you need to bolt another part to your sandwich plate, then you will need to add an insert as shown in the picture on the right. And that insert can be threaded, it can have a nut, it can have various receptacles, but you need to attach this insert usually with adhesive to your sandwich plate and make sure that the local contact stress is high enough. Another important aspect about composite manufacturing methods is the peculiarities of the mounting point of sandwich structure plates. When the structural elements are manufactured to be used in load-affected structures, the connection usually requires an edge where the face sheets are joined and there is no core material between them. The transition has to be smooth without any sudden stiffness changes. Therefore, the core side slopes are created. The angle of the side slope should be as small as possible. It is usually around 30 degrees or even less. You can see it very clearly in the picture below, where the attachment points will have no core material, just the stiff sheet plate. In the following chapter, 4.3, we will discuss core composite applications for gasket and other sealing materials. Gaskets are among the most common and time-tested applications for cork rubber composite. The application of cork composite for their sealing properties in aviation is widespread and proven practical. The gaskets made from cork rubber composites can be used with various fluids and gases in different aircraft systems. In this table, you can see the most common fluid used in aerospace industry. We have gasoline for internal combustion engine aircraft, kerosene for turbojet engine aircraft, engine oil for pistons and engine oils for jet engines, and also we must not forget hydraulic fluid. You can see their standard operating temperatures and standard operating pressures. Because of the different chemical and mechanical properties required for sealing materials used in aerospace applications, quite a few solutions have been developed. The most common solutions are sheet gaskets, solid material gaskets, envelope gaskets, cam profile gaskets, and O-rings. You can see a lot of these examples in the picture below. The properties of cork rubber gaskets depend on a few factors, such as core grain size, density, chemical composition. Adjusting these characteristics makes it possible to create a composite with the required parameters for a specific application. However, it is unreasonable to expect the possibility of making a perfect composite that would perform well in all environments found in the aerospace industry. In the table below, you can see examples of different materials that are used for different applications. For example, in the first row, you can see TS 2050. That is suitable for all engine gears, oils, and coolants. And you can see different materials that are covering mostly all the fluids that appear in aerospace industry. And of course, we must say that these gaskets are time-tested, because during the early era of aviation industry, the first aircraft primarily had piston engines with propellers, and the standard material at that time for engine and fuel systems gasket was cork. The technology of other synthetic materials was not advanced enough to replace it. As time passed, new materials started replacing the cork in gasket manufacturing. For example, as you can see in the picture on the left, there is a silicone gasket. However, as the modern era industry moved towards sustainability and eco-friendliness, aerospace engineers turned their heads back to core gaskets, as you see in the picture on the right. In chapter 4.4, we will discuss the tests of sandwich structure composite materials with cork fillers. The purpose of this analysis was to find the resonance points and evaluate compare a dynamic damping property of differently laminated cork materials. In the current analysis, 4 different objects, 3 made from cork, as shown in the picture below, and 1 made from polymetacrylamide foam. All these core materials were reinforced with glass fiber composite, and the tests were made. The test bench for experimental research is shown below. It includes a metal base with rubber protection for environment low frequency influence, research objects, and a laser scanning system for measuring the vibration of object surface under integrated electronic piezoelectric impulse hammer impact signal. The first conclusion is shown in the graph below. As you can see, in the first analysis, only the cork materials were compared, and they all have a natural frequency that repeats by 20 Hertz. So 20, 40, 60. It means that a natural harmonic frequency was found. And the reason why all these test subjects have the same natural harmonic frequency is probably because of the same reinforcing glass fiber material. However, we can make the conclusion that test subject number 2 showed the best damping results. Therefore, we can conclude that not all grain sizes behave the same way, and we should choose the proper core material for the case that we will be using this. The second analysis was made with the foam material as well. And the conclusion was the difference in the amplitude of materials confirmed that PMI foam is better used for damping an impact impulse than cork material, since the stiffness and deformations of object are different. As you can see in the graph below, the dark blue color is PMI foam, and it has much less velocity amplitude than the cork material. At the same time, the second object shows close characteristics for damping in a few resonance points, which can hold to conclude that laminated cork in some tests can be used instead of laminated PMI foam. What this means is that we can use cork as a good substitute with very close properties. And meanwhile, in aviation, PMI foam is mostly used. However, it is non-recyclable and non-reusable. So if cork material can have very similar mechanical properties, that means it will have quite significant advantage overall. In the last chapter, we will discuss the bending test of cork-based sandwich structure composites. 4 test panels were manufactured to compare different bending characteristics of the sandwich structure panels. 3 of them use different cork-based composite fillers. The main characteristics are presented in table 4.3 that you will find on the left. And one of them contains PMI foam filler. Its characteristics are shown in table 4.4 on the right. So the tests were made pretty similar to the natural frequency tests. The same materials were used. And if you compare the cork materials to the foam, you will see the most significant difference is in the density, because some cork can reach up to 357 kilograms per cube meter, while foam is only 30 kilograms per cube meter. So the foam will be more than 10 times lighter in some cases. You can see the produced materials in the pictures on the left and on the right. Tensile and bending tests were carried out using a Tira Test 23000 universal testing machine with digital test data logging. Catman Express 3 software were used for the data recording. A 3-point bend stand was used. The distance between the fixed bearing was set to 50 millimeters. So on the picture on the left, you see our stand setup that was used for the bending tests. And if we compare the bending results, we can see in the graph on the right that cork material was performing much better than the foam. And also we can conclude that depending on the grain size, we can have very different bending results. For your reference, the foam material is represented by the yellow line in the bottom, and you can see its characteristics were the poorest. Next, we perform the tensile tests. So for tensile tests, we used a CNC machine to cut out a standard testing kit. And interestingly enough, the tensile tests showed very similar results when we compare foam material to various kinds of cork materials. And our conclusion was that it's because the tension force is mostly resisted by the reinforcing fiber, the sheet plates from top and bottom that we use glass fiber for. And therefore, all the materials behave pretty similarly. When we compare it to the bending results, the bending showed very different results depending on the core material. But the tensile results show very similar results for any core material. Therefore, we can conclude that if we need only tensile strength, foam is probably the better material. However, if we need the bending strength as well, or the stiffness, then we should consider cork as a very good alternative. And that concludes our Chapter 4, Manufacturing and Implementation of Cork-Based Composites in Aviation. Thank you very much for your attention. Have a great day.